Here we go. We're starting on short blocks today. We've got measuring tools. We're going to be going over measuring tools so that we can measure piston to cylinder wall clearance, and that's a concept that we can carry over into oil clearance measurements. It's all pretty much the same process. You measure some diameter, then you measure an inside diameter, and you subtract the two, and it's going to give you a clearance. Now, I do apologize. There's a bit of a drone behind me. That's just from a phase converter that's on my CNC mill, and that's going to be part of machining the block. So we're going to start off by introducing the various measuring tools, and what their pluses and minuses are as far as at what level. What tool do we need for what job? And we're going to be considering piston to cylinder wall clearance right now, where it's nice to have a 10,000ths of an inch resolution. So it's entirely possible for a mechanic or technician at a general automotive repair shop to be able to measure these things. Is it necessary? No. But it would be nice to have at least 1,000ths resolution in your measurement to be able to say, okay, I'm either possibly within specifications or I'm definitely way out of specifications for whatever dimension that we're measuring. And again, there's ways that we can do this with these tools that we have in front of us to the best of their ability. But some of these tools, or every tool here, has a limitation. So we're going to go ahead and start by doing an introduction for the various tools, and then we're going to refresh on how to read a micrometer, because I'm sure a lot of people have forgotten that. So here we go. Here we are looking over the various tools that are available to do some measuring. We've got from the most resolution to the least resolution. We'll set them up in this order here. There we go. Let me put this back here. All right, so starting off, a machinist ruler. Every good mechanic needs a good machinist ruler because they're very handy for measuring, measuring things that are really not necessary to get any further than a 64th of an inch. But let's say we're just trying to measure the length of a rod or the length of some component or thickness of some component that's that a fraction of an inch would handle the necessity. But this one here is a machinist ruler. It's called a hook ruler because it's got this hook here on the end. It's got this hook here on the end that allows you to hook it up against something. Say we want to measure the length of this wrist pin. We just bring it up to the end of that. This hook is actually leveled with the bottom of the ruler, and the ruler is a precision ruler, and we can measure out exactly what this wrist pin's length is if we need to be that precise. Now, the machinist ruler it's got a resolution of a 64th of an inch, and that comes out to about 0.156 of an inch. So 15.6 thousandths of an inch or 156 10,000ths of an inch. That's the smallest unit of measure that this machinist rule can measure, which is still pretty small. And it would probably be best if you could use like a magnifying glass or a cell phone so you can take a picture of the measurement and then zoom in on it later. But machinist rulers, especially these quality ones, and this one's made by Starrett. This one is a number 604R. They're really nice. They're also ground across the length of them, so they're not necessarily a precision straight edge, but they're pretty darn close if you're looking for some huge amount of warpage. But a machinist ruler, we can't measure piston to cylinder wall clearance with it. So the next thing we've got, now there's a couple different variations of this one. There is a vernier, which doesn't have any readouts or a dial. It's literally just numbers along the beam, and then there's some numbers on the sliding scale. And those are good. They do require some measurement, and they use the vernier scale design. But then there's this one. The next step up is a dial caliper. And a dial caliper has a dial right here that's going to measure in 1/1000th of an inch. Then there's this one, which is an electronic caliper or digital calipers, where it's capable of measuring less than 1/1000th of an inch. So if I zero this, we can see that we're 0.0000, but that last one is only going to have a resolution of 5/10,000ths. So we can measure something down to 0.5 of an inch in resolution with the calipers. Now, if you want to buy good calipers, honestly, the most durable are the vernier calipers because there's not much calibration to them. So if you drop them, they're usually okay as long as you don't bend anything. Then there's the dials, which are probably most fragile, but they are usually the cheapest ones. And then you have some good digital calipers like this one made by Shars. These are the Aventor calipers, and I've actually been very happy with these. I used to not like digital calipers until I used Mitutoyo brand. Those were just the best ever. And then I took a chance on these Shars, and man, they work really well because you can open and close it, and you can see just about every time. Now, I'm not even using this right, but it goes back to 0 just about every single time. So it has really good repeatability, really good resolution, but this isn't necessarily what we're going to be using to measure piston to cylinder wall clearance. Now, if you're looking to purchase a block, or you're taking an engine apart and you just want to see what size the bore is, you can use these jaws over here. These are the inside diameter measurement jaws, or the inside measurements. And you could bring that out to the bore, and you're going to sweep it a little bit and then go up and down a little bit just to make sure that these jaws are square in the bore. And it's going to tell you if the bore is stock or if it's been bored oversized. But to go any further than that, to say, oh, this cylinder wall has 1/1000th of out of round or something like that, these really aren't what they're made for. But these are very good to have, and I recommend anybody get some. All right, so the next one, which is a micrometer. So micrometers come in different sizes, and if you're going to get the standard ones, you're going to have a micrometer that can measure 0 to 1, so up to 1 inch. And then from 1 inch to 2 inch will be a second micrometer. 2 to 3 would be a third. 3 to 4 would be a fourth, and all the way up to, honestly, you can get them up into 40-something inches big. But in automotive applications, a 0 to 6 micrometer set will do pretty much everything that you want to do. And if you stick with the good brands, you can get them used, and you can actually find new old stock versions of these where somebody purchased them a long time ago and never used them or used them very little. That's how I got these. But what you want is a micrometer that has obviously the normal scale on the front here, but then it has a scale on the side, or on the back side, and this is the vernier. This micrometer is capable of measuring 1/10,000th of an inch, and that's 0.0001 of an inch. This is enough resolution to give us a pretty good measurement on piston to cylinder wall clearance or oil clearance for a bearing and a crankshaft journal. But this guy right here is more than adequate. Now, when you purchase it, you want to make sure you get standards with it, and that'll be a separate box, or it'll be loaded in the box with the micrometers. But it's a set of bars that come with it. There's a 1 inch, a 2 inch, a 3 inch, and all these bars are for, as you put them in between here and you dial it down all the way to 0, and you want to see if the 0 on the thimble lines up with the 0 on that datum, because that bar that you put in there is a standard. This one here you can test with a 3-inch bar or a 4-inch bar. And when you dial this in, if it's a 3-inch bar, the 0 on the thimble and the 0 on the datum should line up perfectly. If not, there's error. I would say if that error is slight, let's say it's a few 10,000ths, just put that error in your calculations and don't try to calibrate the micrometer yourself. Because when you're trying to calibrate 10,000ths of an inch, it gets very finicky. And you're going to be holding it long enough that you're going to affect its measurement. Now, micrometers normally come with these plastic pads right here, and there's a reason for them. They want you to hold it primarily most of its weight right there, because these pads are insulators to keep you from heating up the frame. If I were to hold this thing long enough, its measurements would be smaller than it would be when it were cold. And we don't want that. We don't want a temperature deviation when we're trying to get something that's, say, in 10,000ths of an inch resolution. But regular micrometers are really good to have. The various brands, you've got Mitutoyo, and then there's a couple brands from overseas. Mitutoyo is from Japan, but there's also InSize, which is a good brand that I've used before, and they work really well. Fowler, not too bad. There's also Starrett, but Mitutoyo and Starrett, those are pretty much the best of the best as far as modern micrometers. And you can get some older ones from some older companies, like Brown & Sharp is another good brand. And then you have a micrometer like this one. This one has a capability of measuring all the way down 0.00005. So this is all the way down to 500,000ths of an inch, or a pretty small amount. And this is a rather expensive micrometer, and this is well beyond what's necessary to measure piston to cylinder wall clearance, on top of the cost, because you don't normally buy these in a set. You can, but it's going to be a very expensive set, because this alone is a couple $100 new. It does still have the normal graduations here on the outside, but it's there probably because this is a reused component from one of their other models, and they just put it in this one. And you can see that this one is capable of measuring down to a pretty small amount, and it's normally pretty repeatable. You just have to worry about the feel, because this one has got a ratcheting clutch on the end. Now, I can crank on this more and get it to measure less than that, but that's not the idea. The other benefit with these, in most cases, is that the heat sink is much larger. Okay, so you can hold it longer without affecting the measurement, and some of these will temperature compensate. So as it warms up, it's going to detect it with the thermistor on the inside. It's going to change the measurement on the screen, not to where you notice anything, but it's going to affect the change. Now, there are micrometers that go even further down than this, but this is really overkill already. And those are all tools that we're going to use to measure the outside diameter of something. Like if we're measuring a piston, we need to measure the piston's diameter. We need to make sure we measure that piston in the right spot. We don't want to measure it up here, and we don't want to try and measure it across the pin. We want to measure 90 degrees from the pin and about a quarter to a half inch from the bottom of the skirt. So if we wanted to measure this one, oh, there we go. So if we were asked to measure this one, we have a pad, an area on this piston where we need to measure the diameter. So with the piston here, we're just going to identify this location. So right around in that area is where we're going to put one side of our micrometer, and then the same thing on the other side. We're going to create that patch. Now, you don't have to draw it on the piston. We just want to, we're just trying to identify it right now. So just to review, we want to measure, here's our wrist pin. It's going to go through here, 90 degrees from the wrist pin, a quarter to a half inch from the bottom of the skirt. Now, the reason they do that is because the top of the piston is smaller than the skirt. Because the top of the piston is going to experience a lot more heat, so it's going to expand more. So the top of the piston is considerably smaller than the skirt. That's why we want to measure down here, because this is what size the piston should expand to. So right now, that piston is tapered. Okay, it has a taper to it, and as it warms up on the head of the piston, it should pretty much go out to a square dimension, so it's nice and stable inside the cylinder. So we need to measure the diameter of this piston. There we go. So we're going to put it right here and screw it in. Now, if you use the clutch, that's probably the best way. Now, what I'm going to be doing is I'm actually moving this thing up and down. Okay, and I'm feeling it. There we go. We can lock it, and because it's a cylinder, we can pull it off of it and then take the measurement later. Okay, so that's how we're going to measure outside diameters. How we measure inside diameters. Okay, so let me pull this guy back out. We want to measure the inside diameter of something. We can use our calipers, but remember, they're not very, it is not a very deep resolution. It's only good down to 1/2 10,000ths. But let's say we want to measure the inside diameter of a cylinder. Now here I have a cylinder out of an engine. Okay, so we've got our cylinder here. And I want to measure the inside diameter of the cylinder. Using these tips, I can measure that inside diameter just like this. Okay, so it's 3.6080. So 3.6080 is the inside diameter of this. But there is a better way. So the cheapest method, I wouldn't say the cheapest, but it's probably the most accessible method, is using these telescoping gauges, or telescoping gauges. And what this is going to do, if you see the outsides, they expand out. They're also called snap gauges. They're going to expand out, and what they're going to do is go into the bore and expand to that bore, and then we're going to be able to lock it to that position, then pull it out of the cylinder and measure it with a micrometer. So this is a transfer type measurement. So here, we'll go ahead and give this a shot. So, get that back in there. What I'm going to do is put it down inside the cylinder. I'm going to put it slightly off angle. I'm going to release it, but snug the nut here on the end, or the screw, and I'm going to pull it. I'm going to put it in like this, release the tips, then snug the end here a little bit, and then pull it back through center. And when it does that, the cylinder is going to press these in, and when it gets to whatever the inside diameter is, it's obviously going to stop pushing. So let's give this a shot. Okay. I'm going to snug it a little bit. I'm going to pull it back through center. Now it should have that measurement locked into the plungers. And then we take our micrometer, and we should be able to get a good measurement out of this. And this is saying 3.610, say, or 3.611, somewhere around there. Okay? Now the limitations to calipers, obviously resolution. But the other problem with calipers is I can't measure any deeper than the very top of the cylinder. If I needed to measure to see if that cylinder has taper to it, well, this guy here can do it at the top, the quarter way down, the half, the 3/4, or all the way at the bottom if I had to. And I could take those 4 measurements to determine what taper the cylinder has. So this is capable of measuring down to a much deeper level. The calipers, the dial calipers, they can't do that. So that's measuring the inside diameter of a cylinder with snap gauges. Now the next style is a micrometer, but this micrometer goes on the inside of the cylinder. So these are outside micrometers right here. And this one right here is an inside micrometer. And with it comes a number of tips. So we can see all these different tips that are available. And each one of these are capable of measuring an inch range. So this guy right here is able to measure with just this tip here in the end, is able to measure from 2 to 3 inches. So it can measure as small as 2 inches all the way up to 3 inches. But really, it's only capable in this form to measure up to 2.5. If I want to get to 3 inches, I have to take this tip out, and then I've got to get this sleeve. I'm going to put this sleeve on the tip, and I'm going to put the tip back in there, and I'm going to snug the lock. Now I can measure up to 3 inches. Okay, so let's go ahead and measure our cylinder here. Now we should know that it should be, was it 3.608 to 611? So I need to put my 0 to 1 in here, or sorry, 2 to 3 there. I'm going to use my 3 to 4, but I need to be over 3.5, so I'm going to slide on my 0.5 here, slide it together, and then I just need to press it slightly, then snug the lock nut. Because the way this is going to work is that I'm going to turn this thimble down slightly under my expected measurement. And as I expand it, it's going to push against the walls. Now, it's not going to have a lot of force against the walls. It's just going to have a sliding contact. We don't want to expand the cylinder. We don't want to compress this guy. So I need to take this down to 600. Okay, so this is now at 3.5 plus 100 thousandths, which is 3.6. And we're going to place this down inside the bore, just like this here. And I'm going to expand it out. Now, the way that I like to use it is go to the bore that I'm expecting it to be. Let's say we start with the calipers first. And I'm going to just try and sweep it up and down inside the cylinder. So I'm putting it on one side and I'm sweeping it like this. So I'm going to sweep it up and down inside the cylinder. And if it goes up and down, that means there's more room available inside there. If I can get that set up right. There we go. So let's take it up to 9. Oh, there we go. So I can still sweep it up and down. So it's going up and down. This is hard to do and got a camera on it. Okay, so we're going to go up to 10. I'm going to try and do the same thing. We're going to try and sweep it. Oh, still going. Yep, still got that. And then we're going to go to 11, which is what the telescoping gauge said it was. And it stopped sweeping. So that means the measurement is somewhere in between 3.610 and 3.611. So the telescoping gauge has got us a pretty good measurement. Now, if we wanted to, we could just turn this in just a little bit. Now notice I'm not moving it very much until it just starts to sweep again inside the cylinder. And as a sanity check, I can compare this measurement to the micrometer. And there we go. We're right there at 3.611. So we have some pretty repeatable, we'll call them precise numbers. Are they accurate? It depends on the calibration of these tools. But we can measure the inside diameter with telescoping gauges, with an inside micrometer, and the micrometer over here. Now the next type of tool is quick, and it's usually most often used by the machinists when they're machining the cylinders. But what we have here is a dial bore gauge. Now this one has the measurement end down here. Okay, so our measurement end is here, where we have a small probe tip on the end of it. And that probe tip is actually going to run on the inside of the cylinder. On the other end, we have a nut where we're going to use different length of probe tips. So in the set, we have all these different probe tips. Now this one can measure down to a minimum of 2 inches, and it can measure up to 6 inches because this is 4, but then I also have a 2-inch extension to make it into a 6-inch inside diameter capable dial bore gauge. So let's put that back. Now, the way this works is that when this probe down here gets compressed, you can see the dial on the face sweeps. So what I'm going to do is build the end here. I'm going to put in the correct probe tip for the diameter that we want to measure, somewhere around 3.608. I'm going to stack it up and put it in here and lock it in with the lock nut. And then I'm going to put it in the micrometer. I'm going to set this dial bore gauge here, the dial face, to 0 when the micrometer is at 2.610. And then I'm going to take it out of the micrometer, and then I'm going to stick it in the cylinder. So we should be good with the 3.6. Now this one also has some other adapters up here. It's got a 20 thousandths, a 50 thousandths, and 100 thousandths. I should need to put on the 20. And you see it just goes on the end here. Okay. And then I'm going to set my calipers to the 3.610. Just set it right there. Best I can. There we go. And then I'm going to take the micrometer and sweep. Right, it's kind of hard to do with. There we go. And we should be able to see where that gauge stops sweeping at. And I'm sweeping it inside the probe, inside the tip of the caliper, and I see that I'm at about 15. I'm over here at about 9 o'clock, so I'm going to loosen up the caliper, or the bore face, the dial gauge, and I'm going to run 0 over to this position roughly. Okay. I'm going to put this back into it. I'm going to sweep it again. And it looks like we're pretty close to 0. I'm just going to take a look at it here. Like we're about 1/2 thousandths off, so I'm going to rotate it just a little over 1/2 thousandths and then do it again. About 1/4 thousandths. Okay. When this needle goes over to the 0, that means it goes to this measurement, the 3.610. So we take our cylinder, and I'm going to put the probe end down here, down inside the cylinder, and I'm going to sweep it. And we're going to see, look at that, it's showing right there. Let's see if I can get in closer on that. Okay, so right here is it at its biggest, and I'm going to pull it through center, and it's compressing the probe. And you're going to see that it stops a little around, somewhere around the 1/2 thousandths. And rotate there. There we go. Well, it's, there we go. So it's stopping somewhere around the 1/1000th. Now, as the probe tip gets depressed, it's indicating smaller and smaller and smaller and smaller and smaller. And remember, we are now 1/1000th of an inch away from the 3.610. So it looks like our actual measurement for this cylinder is going to be 3.611, like the telescoping gauge showed, like the inside micrometer showed, and like the dial bore gauge showed. And if we think back to the calipers, it said 3.608. And 3/1000 of an inch is huge when it comes to piston and cylinder wall clearance. So the benefit to a dial bore gauge is how quick it is. So if we needed to measure this cylinder and we wanted to measure to see if there was taper, I could easily stick this dial bore gauge in at the very top, and then I could stick it in further, and there, and then all the way out here. And that's how we measure cylinder bore with the dial bore gauge. So the next thing we're going to do is actually do the measurement on our engine. It's up on the CNC machine. And once I get all that set up, we'll be back. Here we are over at the engine. Now this is mounted up on the CNC machine. It's getting ready to get bored and surfaced, and that'll be next video. So I have one piston, and I've just decided to go ahead and grab a single piston. We can measure piston and cylinder wall clearance on all the cylinders, but in this application it's not necessary because we're just doing this as a matter of education. So let me go ahead and remove the piston rings because they're kind of getting in my way. There we go. Now I didn't show another method of piston to cylinder wall clearance measurement because I didn't have everything out on the table, and this method works best when I have both the cylinder and a piston that fits in the cylinder, and that's going to use feeler gauges like this. Now this isn't a complete set. This should go all the way down to 1.5 thousandths of an inch, but it's just a demonstration. So if I take my 2 thousandths feeler gauge and I'm going to put the cylinder or the piston in the cylinder, now notice before I do that measurement, this piston has a huge amount of play up here in the top. There's probably a 1/16 of an inch or more of piston play in the top. But as I lower this piston down into the cylinder, that play goes away, because remember, the piston is larger right here when it's cold, and that's when we handle the piston. So let's go ahead, and what I'm going to do is try and stick a 2 thousandths feeler gauge in between the piston and the cylinder wall, and I want to make sure if that piston, there we go, it easily slides up and down with 2 thousandths of an inch, so that means my piston to cylinder wall clearance is at least 2 thousandths. Now the next one I'm going to try, I'm going to step up to 2.5 thousandths feeler gauge. I'm going to do the same thing. Now this method works really good if you're trying to find out if an engine is good to buy, or maybe you're doing a quick inspection to see what the piston and cylinder wall clearance. So this piston moves up and down very easily inside that cylinder with a 2.5 thousandths feeler gauge. So let's step up to 3 thousandths, and we're going to go up until we can't get the piston up and down inside the cylinder. There was 2.5, and now we're going to use 3.5 thousandths. It's still moving pretty easy, so we've got 3 thousandths of an inch cylinder wall to piston to cylinder wall clearance. Now I bet if I go up to 4, it's probably going to be too tight to move easily. So let's put that in there, and I'm making sure I'm going in the middle of the skirt right here. That's where our wear measurement is, or our piston to cylinder wall clearance measurement is. And I put that 4 in there. Yeah, the piston's not going anymore. So my piston to cylinder wall clearance, we're just going to say is 3 thousandths of an inch, which is probably 2 times bigger than the service limit that GM specifies. So the cylinder is either oversized, or the piston could be undersized by that amount. And because this cylinder actually has some scuffing here on the side, it's possible that the diameter of the piston is reduced. All right, so that's done. Let's go ahead and do a quick measurement on our piston to cylinder wall clearance. First thing I need to do is measure the diameter of the piston. So using the micrometer, I'm going to measure this piston outside diameter. Notice I'm a 1/4 to a 1/2 inch from the bottom of the skirt. I'm just going to wiggle it up and down. There we go. Slide it off. And our measurement comes out to 3.777. Okay, so this is coming out to 3.777. And I'm just writing it here on the block. Now, it's actually not exactly 3.777. I'm just kind of estimating on this right here because it's closest to the 0.002 mark. And really, with the method that we're going to be using, what this says doesn't matter because we're looking for a calculation between an inside diameter and an outside diameter. And that calculation is going to be done by transferring this dimension to the dial bore gauge. But let's go ahead and just read it. So the actual measurement on this micrometer comes out to 3.776. And our 10,000th place is an 8. There we go, 3.7768 is the actual. Now, because I've locked this into position, I'm going to get the dial bore gauge and set it. So we've got our dial bore gauge. I'm going to put it in between the anvil. There we go, and I'm going to sweep it, and I'm looking up at the gauge. Okay. I've eyeballed about where it's at. I'm going to move the 0 around, and I'm going to set this to the diameter of the piston. Now, if the cylinder is bigger, that means that the needle will go past 0. It will go past 0, and whatever it indicates on the dial will be the literal piston to cylinder wall clearance. So we have it pretty well set there. So I'm going to take the dial bore gauge, lower it down to the bottom there, raise this up. All right, so here we are. Here we are at the bottom of the cylinder. This is the bottom of the piston travel. Try and get the glare off the screen. All right, so let's measure it. And we're coming in at about 3.5 thousandths. Each one of the large marks is 1 thousandths, and then the smaller marking in between is 0.5 thousandths. So let's see if we can get that to repeat. Yep, so we're at about 3.5 thousandths of an inch, which is pretty much what the feeler gauge said. It was 3 thousandths, but it wasn't 4 thousandths. So it was somewhere in between those two. Now, to get our different dimensional measurements, because we want to know if the cylinder is tapered or if the cylinder is out of round. To determine if a cylinder is tapered, we're going to measure it at multiple heights or depths. So we're going to measure it at the top of the cylinder, measure it at the middle, and then measure it at the bottom. And we're going to record those measurements. So taper is at different depths within the cylinder. Cylinders will usually be bigger in the top. Cylinders will usually be bigger at the top than they are at the bottom. And to get the original dimension, what we're going to do is actually turn the gauge sideways in line with the crankshaft. And at the bottom of the cylinder, this will usually give us the original bore diameter. So let's go ahead and do these measurements, and we're going to record them go. Let me get onto the other side here. Okay, so our first measurement at the very top of the cylinder, we're going to have our most piston to cylinder wall clearance. All right, so now this is also a measurement 90 degrees from this feeler gauge measurement. So I'm getting just over 4.5 thousandths. So 0.0045. We go down to the middle of the cylinder, getting right at 4 thousandths, and going down to the bottom of the cylinder, getting right at about 3.5 thousandths. So our cylinder has a 1 thousandths taper, so that's 0.001. The top of the cylinder is bigger than the bottom of the cylinder by 1 thousandths of an inch, and that's how we measure for taper. To measure for out of round, we're going to measure in this direction and then turn the gauge 90 degrees. So let's redo this measurement. So our top measurement was right at 4.5 thousandths. And then I'm going to turn the gauge 90 degrees. I'm going to measure this dimension. And this one is 3.5 thousandths. So that means that this cylinder is smaller in this direction than it is in this direction. And that's the normal wear pattern, where it's bigger at the top and then it's larger 90 degrees to the crankshaft. This is our worst measurement by far. So our cylinder has 1 thousandths taper and it has 1 thousandths out of round. And that's how we do our piston to cylinder wall measurement. So let's check this next cylinder. Let's do our bottom measurement. See if we can zoom in on this. See if you can play at home. All right, so let's sweep it. Let me turn that to where you can see it. So I'm seeing about 3.5 thousandths, maybe a little bit less. And we're going to do the top measurement. Hopefully we don't get too much glare on this one as I sweep it this way. It looks like about 4 thousandths. Now granted, I'm actually turned a little bit, so about probably 30 degrees to one side just for filming. So as I sweep this, I'm getting about, I can get that back in the shot. Getting about 4 thousandths. So down at the bottom it was 3.5, almost 3, and then at the top is about 4 thousandths. So in this cylinder, about 90 to 45 degrees from our thrust measurements, we have about 0.5 thousandths of taper. And that's how we measure piston to cylinder wall clearance.